Our first circuit is a series circuit. How do we identify a series circuit? Seth?
Well, the resistors are in series.
Okay, what do you mean by that?
There's only one way for the electrons to go.
There's only one path, there's one loop. If I was to look at the electrons flowing from my battery, we have current flow from minus to plus. There's only one path. So we've determined that this is a series circuit. What is the formula to solve R total in a series circuit? Here? Add them up. Series resistance is R1 plus R2 plus R3. If there was 4 resistors, plus R4. If there was 10 resistors, add them all up. So we have 10 ohms, 20 ohms, and 30 ohms. So we have an R total of, I heard somebody say it, 60 ohms. My E total I've already given in our diagram, correct? E total, electromotive force measured in volts, 10 volts. How do we come up with I total? Ohm's law. I is what? E divided by R will give us current in amps. 10 volts divided by 60 ohms. Yes. 0.166 amps, which is the same as, what's the correct way to express this, Seth?
166.
Very good. Using engineering notation, it's 166 milliamps. Little m, capital A. What is our formula for power? Somebody other than Seth. David?
Okay, E times, okay, I'm trying to remember. I times E equals P.
Very good. Power is volts times amps. I times E or E times I. So we're going to take 10 volts, times it by 0.166 amps, and what do we come up with? 1.666 watts. Our 4 main parameters have been solved. We've used Ohm's law, came up with E total, I total, R total, and P total. As long as they're correct, we can now use these numbers and the information that we have to hopefully solve the rest of our problem. Now, when we solve our voltage drops, what should they do in the end? What law am I talking about? Like if I take my voltage drop across R1, R2, and R3, what should we come up with?
E total.
I want to come up with E total. Who says that? What law? Kieran? Kirchoff's law. The sum of all the voltage drops in a series circuit, some people say a loop, adds up to the applied voltage. So my voltage across R1, R2, and R3 should add up to E total. When I say voltage drop, that means I took a voltmeter and I put it across R1. We'll call this R1. I put it across R2 and I put it across R3. Those voltage drops should add up to E total. Now, without solving it, what can you tell me about the voltage drops? Which resistor is going to drop the most voltage? R3. Why? Because it's the most resistance. The largest resistor is going to drop the most voltage. The 20 ohm is going to drop less, and the 10 ohm is going to drop even less. Let's try it. How do we solve ER1? Well, again, if I'm looking for the voltage drop across R1, it would be I times R. Now, R is what? R1 is 10 ohms. What am I multiplying that by? I heard somebody say it. Okay, where did you get that from? You're right. Okay, I total. Because what law states that? That would be Kirchoff's current law. And what is that? The current is consistent, or current is constant in a loop or a series circuit. So we know that no matter where I put an ammeter, if I was to break the circuit and put a current meter here, or here, or here, or here, or back here, it would always read 0.166 amps or 166 milliamps. Current is constant in a series circuit. So I can use that constant current and multiply it by each resistor to come up with each individual voltage drop. So we're going to take 10 ohms and times it by 166 milliamps, and we're going to come up with 1.66 volts. What are we going to have for 20?
12
times 20 ohms, and that's going to give me 3.32 volts. And I'm going to do the same thing for ER3, 30 ohms times 0.166 amps, or 166 milliamps, 4.98 volts. Now, let's rewind a minute. I said that Kirchoff's law should state what? The sum of all the voltage drops should add up to
E total.
E total, or the applied voltage. So let's take 4.98 plus 3.32 plus 1.66. We end up with 9.96, close enough. We obviously rounded off a little bit, so I'm right up at 10 volts. So does that tell me it looks like so far I've done everything right? Do these numbers agree? Didn't we say that R3 was going to drop the most and that R1 was going to drop the least? Well, R3 dropped almost 5 volts, 4.98, and R1 dropped 1.66. That was the least. So far everything's working out in our series circuit. Now, what about IR1? How do I solve IR1? There's two ways I can solve it. Alonzo? Okay, so you're stating Kirchoff's current law. Current is constant in a series circuit, so Alonzo's like, I know the law, I don't need to solve it. I know that this is a series circuit, and that no matter where I measure my current, it's 166 milliamps. So he says, what the heck? Let's put it in there. He's right. Could I solve it? Well, I equals what? E divided by R. So could I have done ER1 divided by R1? I would have came up with the same answer. I could have also done ER2 divided by R2 and ER3 divided by R3, and I would have still come up with 166 milliamps. Power. How much power is being dissipated in resistor number 1? Because we know that we have current, we have voltage, and when we have current and voltage, we have power. Is this resistor consuming power in the circuit? It sure is. How about this one? And how about this one? What should happen with all my powers? If there's no other things in the circuit, all the power being dissipated in each resistor, PR1, PR2, and PR3, should add up to my power total of 1.666 watts. We agree with this? Okay, how do I solve it? Seth?
Take ER1 divided by IR.
Okay, the formula for power, as David said earlier, is volts times amps. So what you're going to do is you're going to take the volts of R1, because we're talking about ER1, and we're going to times it by the current through R1. So we're just going to plug the numbers into the formula. ER1 times IR1 equals PR1. Let's try it. 1.66 volts times 166 milliamps equals 275.56 milliwatts. Little m, big W. PR2 would be what? ER2 times IR2. 3.32 volts times 166 milliamps, and we end up with 551.12 milliwatts. And then PR3 would be ER3 times IR3, 4.98 times 0.166, and we end up with 826.68 milliwatts. Hang in there. Okay. How do we know we're right? How do I know if I did PR1, PR2, and PR3 right?
If they add up to B total.
They should add up to B total. 275.56 plus 551.12 plus 826.68 gives me 1.653 watts, and again, I rounded off, so we're pretty close. That says 1.66 watts. I came up with 1.653 and a bunch of numbers. Everybody agree? Okay, so that's our series circuit. Now, I'm going to take my same 3 resistors. Let's erase all these numbers. I'm going to take my same 10, 20, and 30 ohm resistor, and I'm going to wire them in my circuit differently. Same 3 resistors. This is R1, this is R2, that is R3. R1 is 10 ohms, R2 is 20 ohms, and R3 is 30 ohms. What can you tell me that's different about this circuit? Nicole?
Never mind.
Never mind. Okay, it's a parallel circuit. How do you know that? How do you know by looking at it that it's parallel? Because they're next to each other? No, that's not always the best way to go. Because I could have made them go like this and not connect them. And just because they're next to each other, they're physically parallel to each other, doesn't necessarily mean that they're wiring a parallel circuit.
Because if you chase the electrons, there's more than one path.
Okay, he's chasing electrons. He's following my electrons, and we got a fork in the road here. I can take multiple paths. Here's one, here's another one, and here's another one. And where they meet back is where it becomes a series circuit again. So in this case, there really are no other parts in the circuit. So this circuit, all 3 resistors are in parallel. So what's going to be different about this circuit? Well, let's talk about that. Earlier, we took a voltmeter and we went across R1, R2, and R3 in our series circuit. And all those voltage drops were different because each resistor had a different amount of ohms, different amount of resistance. What's going to happen if I take a voltmeter and go across all 3 of these resistors here?
It's always going to be the same.
It's always going to be the same. Very good. If I took a voltmeter and I put my minus here on the negative of the battery, put my positive here, I'm going to measure 10 volts. If I slide it down this wire, I'm still on the same wire. I'm still on the same part of the circuit. So no matter where I put that meter, I might be physically across R2, R3, R1, but they're on the same part of the circuit. So each one of these resistors are dropping 10 volts. So kind of like Alonzo when he said current's constant in the series circuit, and we threw IR1, IR2, and IR3 in there, we're going to do that for this. Except we're going to do it for the voltage. Because ER1 is 10 volts, ER2 is 10 volts, and ER3 is 10 volts. What is E total? 10 volts. Can't solve I total until we have R total. Okay, how do we solve for our 3 resistors in parallel? We're going to use the reciprocal method. We're going to stick it in our calculator, and we're going to use the X -1 button. So I'm going to take 10 ohms, X -1, plus 20 ohms, X -1, plus 30 ohms, X -1. We're going to come up with that answer, and then we're going to hit X -1 again. That's our reciprocal. And we're going to come up with 5.454 ohms. What's up?
This is for you.
Thank you, sir.
Mr. Doug wants to know.
Okay, 5.454 ohms is our R total. How am I going to come up with I total? David?
Coming up with I total, it's E divided by R.
Very good. I, Ohm's law, E divided by R. I is E over R. 10 divided by 5.454. And that's going to come up with 1.833 amps. 1.833 amperes of current. Power is volts times amps. Ohm's power law. 10 times 1.833 is going to be 18.33 watts. Now, how do I solve IR1, IR2, and IR3? Nicole?
You do R1 divided by resistor 1?
Okay, so I want to take I would be E over R, right? But we're talking about R1. So we're going to take ER1 divided by the value of R1.
Oh, yeah.
So ER1 is 10 volts divided by 10 ohms, and that's going to give me 1 ampere or 1 amp of current. IR2 would be what? ER2 divided by R2. So 10 volts divided by 20 ohms would be 0.5 amps, which is the same as, engineering notation, 500 milliamps. And IR3 would be 10 volts divided by 30 ohms, which would be what? 0.333 amps, or 333 milliamps. How do I know if I'm correct?
If they add up to the total
Total what?
current.
Very good. IR1, IR2, and IR3 in a parallel circuit should add up to I total. 1, 0.5, and 0.333 should add up to 1.833. So that worked. What about PR1, PR2, and PR3? What do we do there? Seth?
Do, the first one is ER1 times IR1.
Okay, plug and chug again, just like the last one. PR1 is always ER1 times IR1. So 10 volts times 1 amp is 10 watts. PR2, 10 volts times 0.5 amps is 5 watts. And PR3, 10 volts times 0.333 amps would be 3.333 watts. And then we can add them up and we should come up with P total, which is 18.33 watts. And that looks like it worked out. Okay, so that's our parallel circuit. Now we're going to take the same 3 resistors and we're going to do a complex circuit, or a series parallel, or combination, or whatever you want to call it. So let's erase these answers one more time. Dakota,
Yeah,
come to the board.
sure.
I'm going to let you draw me a complex circuit with a 10, 20, and 30 ohm resistor. Okay, there's R1. Little meter. There you go.
Squiggles,
Okay.
not a thing.
Okay. Which one's going to be the 10? You want that to be the 30? You want that to be the 10? And that to be the 20? Okay. Dakota writes in hieroglyphics, so what I'm going to do is I'm going to neaten this up a little bit so everybody
for
can
it.
see it. He put his 30 ohm resistor in series, and he has the 20 and the 10 in parallel. Let's try to make this a little easier.
You do squiggles?
Zigzags.
Mine are squiggles.
Okay, R1, R2, R3. You wanted this to be what, the 30 ohm?
Yes.
R1 is 30 ohms, R2
20.
is going to be 20 ohms, and R3 is going to be 10 ohms. Okay, so we are going to determine which resistors are in parallel and which resistors are in series. How do we do that?
Magic.
Follow my electrons. Seth, what's happening here?
There's flipping road, we have to teach you.
Okay, exactly. So I got 2 paths here. I can go through R2, I can go through R3, and then they meet back here. So we have a 20 ohm and a 10 ohm resistor in parallel. So we've identified and isolated our parallel. We now have that in series with R1. There's no other series resistors. So what are we going to do?
Add up the R2 and R3 parallel.
Parallels, do we add them up?
No, you have to unite it first.
Okay, we're going to do the reciprocal of R2 and R3. And we're going to assign that what? What do we call that? There's a term that we use. We want to assign it what? David?
I'm trying to think. It was called the. Oh wait, the resistance equal total.
Okay, R equivalent. We call it equivalent
Yeah,
resistance or R equivalent.
Trying to
Because
remember.
this parallel feels like a single resistor in this circuit. So we want to assign it an R equivalent. So let's do that. R2, 20 ohms, x negative 1, plus R3 is 10 ohms, x negative 1. X negative 1 it again, we come up with an R equivalent of 6.666 ohms. That's my R equivalent, REQ. What are we going to do next? Say that again? Add them up. My 30 ohms plus my equivalent resistance, so my R total is going to be 36.666 ohms. Nothing's changed, my battery's the same, so we have 10 volts. And we're going to solve our current. I is E divided by R. So 10 volts divided by 36.666 ohms gives me 272.73 milliamps of current. 272.73 milliamps of current. Let's do our power. 10 times 272.73 milli would be what? E times I, which would be 2.7273 watts. ER1, ER2, and ER3. Now this is where it gets a little tricky. This is where people tend to make a couple of mistakes. If I was to take a voltmeter and put my leads across R1, I'm going to measure some voltage drop, right? And then if I take my leads and put them across R2, I'm going to measure some more voltage drop. And then I slide them over to R3, that's going to be the same, right? So R2 and R3, the voltage drop is the same. That's why I like to put them together. Because later on, when we do Kirchoff's law to check my math, we know that the sum of all the voltage drops in a series circuit equals the applied voltage. Well, we've simplified this complex circuit. It's now a series circuit with a 30 ohm and a 6.666 ohm resistor. So the voltage drop across both of these, plus the voltage drop across this, should add up to that. Follow me? Okay, how do we solve it? Current's constant in a series circuit, so what do we want to do?
Find ER1 first.
I want to find ER1, and how would you do that?
IR1 times R1.
Very good. Value of IR1, which is I total, because current's constant. 272 milliamps, 272.73 milliamps. We're going to multiply that by our 30 ohm resistor, and we are going to come up with 8.1819 volts. ER2 and ER3. This is where some people will make a mistake. Do not use these resistances. We're going to use our equivalent, 6.666 ohms. So we're going to take 6.666 ohms. We're going to times it by our constant current of 272.73 milliamps, and we're going to come up with 1.818 volts. And what did we say about this and this? It should add up, just like Kirchoff's law, to 10. 8.1819 and 1.818, sure enough, is close enough to 10. 9.9999, there you go. Now, how do I solve IR1? Well, IR1 is the series part of the circuit, so I'm going to do what Alonzo does. And what do you do, Alonzo? He doesn't solve it, you follow the law. Kirchoff's law, current is constant in a series circuit. So we know that the constant current of 272.73 milliamps. Could I solve it? Sure. I could take ER1 and divide it by R1 and come up with the same answer. Now, does that work for the current through R2? Okay, what I need to do is take ER2 and divide it by R2, not R equivalent, because now I'm doing currents through individual resistors. So we're going to take ER2 and divide it by 20 ohms. ER2 was 1.818 volts. divide that by 20 ohms, and that's going to give me 90.9 milliamps. 90.9 milliamps. Same thing for ER3. If I take ER3, which is still 1.818 volts, what are we going to do with that?
Divided by 10.
And we're going to come up with 181.8 milliamps. And if you add them up, that will add up to that, the constant current. Does that make sense?
Sure.
Okay, how do I solve my powers? Seth, you're my power guy.
Do, ER1 times IR1?
Exactly, plug and chug, put the numbers right in the formulas. Power is always volts times amps. ER1 times IR1, ER2 times IR2, and ER3 times IR3. So we're going to take 8.1819 volts, we're going to times it by 272.73 milliamps, and we're going to come up with 2.2314 watts. ER2, 1.818 volts. We're going to multiply that by 90.9 milliamps. And we come up with 0.1652 watts, or 165.2 milliwatts. And then ER3 is also 1.818 volts. We're going to multiply that by IR3, which is our 181 milliamps. And we're going to come up with 0.330 watts. And of course, if we add them up, that'll get me up to my 2.7 watts. That's our complex circuit. That's the one that everybody trips up on. Little harder, a lot of little extra steps. If you follow the rules and follow the laws, you'll get there. But in the end, we always want to do what? Kirchoff's law to make sure we come up with E total, make sure our current law works out, make sure our power law works out. At least you can go back and check your work, and if it doesn't work out, you can back up and say, okay, where did I, try to figure out where you made your mistake.